Welcome to the next learning unit in the chapter Solar Inverters. In the last unit you got to know the basic ideas of MPP tracking. Here we will now deal with the actual core task of the inverter, converting direct current into alternating current. But what does direct and alternating current actually mean? In direct current, the electrical current flow moves in a single direction. In contrast, with alternating current, the direction of the current flow changes at regular intervals. Only some consumers, for example a battery, can be operated with direct current. Other loads, such as a drilling machine, a refrigerator, or even the public power grid itself, cannot simply be connected to PV modules. This has historic reasons. In the past, turbines powered by fossil fuels or nuclear energy turned generators which produced an alternating current. Hence, the public grid became an AC grid. If we want to use PV modules for any device in the household, or to feed electricity into the current public grid, we have to somehow convert the direct current into alternating current. To understand the basic principle of converting direct current into alternating current, let's first look at a very simple circuit, the full bridge inverter. In this circuit there are 4 switches, S1 to S4, which are each switched alternately in pairs. A load is connected between the switches. There are basically 2 switching states in the circuit. To better understand the circuit, let's take a closer look at the 2 switching states of the circuit. In the first case, the switches S2 and S3 are open. The current flows through the switches S1 and S4. In the second case, the current flows through switches S2 and S3. Pay attention to the direction of the current through the load. This is the opposite of the first switching state. The direction of the current at the load changes with every switching process. This reversal of direction can also be observed on an oscilloscope. For this purpose, the voltage between the input and output of the load is measured continuously. We see that a square shape alternating current is generated by this circuit. This square wave signal repeats itself continuously. The number of times it is repeated per second is called frequency. The frequency of the voltage indicates how often the wave repeats per second. In North America, the typical line frequency is 60 Hz. In Europe and large parts of the world it is 50 Hz. This means that the wave repeats itself 50 times per second. The polarity changes 100 times per second. With this circuit we can now generate a square wave alternating current with the appropriate frequency. But to connect the inverter to the public grid, we need a sine wave alternating current. A square wave current would generate numerous harmonics. Hence the grid gets polluted with so-called noise, waves with a multiple of the sine wave's frequency. These harmonics could damage the connected loads. We will deal with the topic of harmonics in more detail later. So we need a sine wave instead of a square wave. But how can we convert a square wave alternating current into a sine wave? The sine wave alternating current can be characterized by the fact that the voltage does not rise and fall suddenly, but gradually changes its amplitude. This means that we have to be able to somehow adjust the amplitude of the voltage. For this purpose, the so-called pulse width modulation, or PWM for short, is used. The basic idea of the PWM is the following. If you chop a DC voltage into short pulses, for example by opening a circuit periodically for a short time and then closing it again, you can get a pulse signal that has a lower voltage on average. Of course, the output signal still has to be smoothened in order to obtain a uniform voltage rather than a pulsed one. In the example shown here, a 12-volt DC voltage is converted into a 3-volt voltage on average. The amplitude of the output signal depends on the so-called duty cycle. The duty cycle is the ratio of switch on time to the period duration. In the case shown, the duty cycle is 25%. If the duty cycle is increased, the amplitude of the output signal also increases. The trick with pulse width modulation is to chop up the DC voltage into pulses of different widths. In the case shown here, the switching frequency, that is the number of pulses per second, is 10 times the frequency of the desired output signal. One period of the sine wave signal is made up of 10 individual pulses. The duty cycle is adapted so that voltage and current follow the sine wave. However, with the switching frequency shown, the sine wave can only be recognized to some extent. The accuracy of the approximation can be increased by increasing the switching frequency. Here you can see the signal that results from a 32-fold switching frequency. With a signal frequency of 50 Hz, this corresponds to a switching frequency of 160 Hz. Of course, no mechanical switches are used in modern inverters. The desired switching frequency cannot be achieved with these. Instead, electronic switches such as MOSFETs or IGBTs for higher powers are used. They have maximum switching frequencies of several 10,000 Hz. With a desired frequency of 50 Hz, each period can be chopped into 200 or much more pulses. With these MOSFETs, the switch pairs S1 and S4 or S2 and S3 are now opened and closed several times in quick succession. The voltage signal is chopped into several pulses with different widths for each switching state. This is done by changing the duty cycle to adapt voltage and current to the sine wave of the grid. If the switching frequency is sufficient, this circuit can simulate a very precise sine wave. We can also display the circuit just explained in a slightly different way. It's still exactly the same circuit. We have a solar generator consisting of one or more modules, a bridge circuit that generates an alternating current from the direct current, and a consumer. In order to generate a sine wave from the pulsed voltage signal, the signal has to be smoothened. For this purpose, a low-pass filter is integrated into the circuit between the consumer and the PWM bridge. Such a filter usually consists of inductors and capacitors, although several of the two can also be included in the filter circuit. Instead of operating a consumer, we could, of course, use the inverter to feed electricity into the public grid. This does not change anything in the circuit. This circuit now has to be supplemented by a further link. For a better understanding, let's first take a look at the performance of the inverter. A more or less constant direct current output of the solar generator is applied to the input. The inverter supplies a sinusoidal voltage at the output. The power is also sinusoidal and oscillates back and forth between 0 and a maximum value. So, there's a difference between input and output power at almost every point on time. This differential power has to be buffered somehow. In order to temporarily store the DC energy, a capacitor is integrated into the circuit between solar generator and the PWM bridge. This is also known as DC link. Since the power on the AC side drops to 0, this capacitor must have a very high capacity. So relatively large and expensive capacitors are required. However, this only applies to a single-phase inverter. This picture is more favorable for a three-phase inverter. We will take a closer look at the three-phase inverter. The circuit just discussed generates a single-phase sine wave alternating current, that is, a single sine wave voltage signal. Most public power grids carry 3 such alternating currents. These 3 alternating currents have the same voltage and frequency, but their phase is offset by 120 degrees from one another. A single-phase inverter inevitably feeds all of the electricity into one of these phases. In the case of a larger system, this can lead to asymmetries between the phases. However, such asymmetries should be avoided in practice. Therefore, three-phase inverters are usually used for larger PV systems. Such an inverter divides the current evenly over all 3 phases. The bridge circuit of a three-phase inverter is very similar to that of a single-phase inverter. We have the solar generator, a capacitor for intermediate storage, a bridge circuit, filter, and the grid connection. In the PWM bridge, 6 instead of 4 switches are used. With these 6 switches, 3 sine wave alternating current signals are generated by a sophisticated switching rhythm. The power curve at the output of the three-phase inverter is much more favorable than that of a single-phase inverter, because the sum of the power of all 3 phases is important here. The sum is almost constant, so that much smaller capacities are necessary for intermediate storage in such an inverter. Let's summarize this unit. The direct current from a solar generator is converted into alternating current by a bridge circuit made of electronic switches. The pulse width modulation is used to approximate a sine wave. The pulsed signal is smoothened by an LC filter. Since the output power is pulsating, a capacitor is installed on the DC side of the inverter as a buffer. For larger systems, three-phase inverters are used, which divide the input power into 3 phases. I thank you for your attention.